Alright, hey, I'm gonna try to do the cylinder video tonight too. My kitten is up and about, so there may be interruptions. We'll find out. Anyhow, again, I know we've already done the first one, we've done 27, but I'm just gonna do it again so they're all here. So let's go. Excuse me. Alright, so it says a tank in the shape of a right circular cylinder is filled with water. The tank stands upright and has a radius of 20. Find the rate of change of the height of the water in the tank when the water is being pumped out at a rate of 25 cubic centimeters per second. So again, what do we got to know here? You got to know that, oh, that shouldn't be blue. That should be anything but blue. Alright, to make a cylinder, you take a couple of these here ellipses and you connect the dots like so. So let's call that the actual water. Well, that water has to go into something, right? So that'll be the container. Duplicate. If this is my container, I'll make it thicker. We'll make it, I don't know, green. It's a green container. And we'll put the water inside of there. Yoink. I don't know what I'm doing here. Alright, anyway, here's what I wanted to remind you of. Simply that as the water goes up and down, obviously the height is going to go up and down as water is drained away or as water is pumped back in. The height goes up and down, but because this thing is a cylinder, as the water drains out, that radius is not changing. For this problem at least. And we talked about this in class, how for different problems, maybe you have a cylindrical block of ice that's melting. Maybe the radius does change. Maybe the height changes too. But when you're talking about water that's just in a canister that's shaped like a cylinder, dRdt is often just going to be 0 for you, which is going to greatly simplify some of these problems. So hopefully that idea is hitting home and making sense. But let's go ahead and just dive in. This is going to be a lot like cones, where the formula for our volume is a lot like the formula for the volume of a cone. For a cone, volume was 1/3 times pi r squared times h. And so the only difference for a cylinder is we lose the 1/3. It's just pi r squared h, and that's going to be our formula. Now, notice we've got the r, we've got the h. For problems like this, we often do need to leave the r and the h in here. So that is going to mean that when we do our differentiation, we'll have to do product rule. So I usually just lump the pi in with the r squared and let the h do its own thing, and then think of this sort of as my a and my b. And just remember that product rule means that the derivative of v would be derivative of a times b plus a times the derivative of b, which for us means that we're going to get a dv dt. Then we're going to go 2 pi r times the dr dt, because we're chain ruling that out. But then we multiply by just plain old h, so there's a factor of h in this term too. All of this, by the way, is just multiplication. It's a 2 times a pi times an r times a dr dt times an h. All of that stuff is just multiplying. Then you add to that your a, which is pi r squared, times the derivative of h, which is just a dh dt. And again, that's all multiplication too. So look in here, there is an r, there's a dr dt, there is an h, there's a dh dt, there's a dv dt. The one thing we don't seem to care about is volume again. The actual volume seems to be not needed. Pretty much across the board, we just never need it. Now I will say for this problem, since we all agree that the radius isn't changing, that makes dr dt go to 0, which means this whole term basically goes to 0, which means only this term is going to matter for us. So from here we'll go forward. Okay, cat interruptions are happening. Alright, so what's happening? We've got, I don't know, dv dt. Alright, so we agreed that Water is being pumped out at a rate of 25, so that means dV/dt is negative 25. We said this whole term is going to 0, so I don't care about the r, the dr/dt, the h, none of that matters because dr/dt is 0. Then in the second term I've got a pi. I do need my radius, which they gave me. They said it was 20. So we'll plug that in, we'll square it. And then dH/dt is what we're solving for, the rate of change of the height. So this is a negative 25. That equals 400 pi times dH/dt. So if I bring this way over here to make some more room, we're going to get an answer of negative 25 divided by the 400 pi, which I can reduce down to negative 1/16, negative 1/16 times pi, and that'll be dH/dt. So do that and then give me a decimal to go with it. So 1 divided by 16 pi, I'm getting 0.0199. And again, just include your units. Since this is the rate of change of the height, it'll be plain old centimeters per second. And there's everything for that one. Okay, and we said in class that 28 was really similar, but I'll go ahead and do it for you this time again if you need me to. So what's happening this time? We've got water flowing into a water tower at a rate of 8. So that means our dV/dt is positive this time because we're gaining that volume rather than losing it. So dV/dt is 8. How fast is the water level rising? So that means we're trying to solve for dH/dt again, just like last time, which is normal. If the cylinder's radius is 4, so they're saying the radius is 4. That's a question mark. So again, we know that dr/dt, it is going to be 0 because again, as the water level rises in the cylinder, it's not getting wider or shrinking down smaller. The radius is staying the same. So dr/dt for us will be 0, which means we should get the exact same derivative we had before, which was dV/dt equals, what was it from before? This same thing, 2 pi r dr/dt times h, but again, that whole term will go to 0 for us. So it's 2 pi r dr/dt times h, and then plus pi r squared dH/dt. So since this problem is basically the same situation, we again know that that's 0. So that whole term goes to 0, which means we'll just plug in our dV/dt, letting it be 8. This guy essentially is just gone. So we get pi times the current radius, which is 4, times dH/dt. And so solving this gives us 8 divided by 16 pi, aka 1 divided by 2 pi, which is some decimal. What have I done? Oh man. Okay, 0.159. And again, since this is the rate of change of the height, it's going to be in plain old feet and minutes, so feet per minute. So that's it for that. Now 29 I think we did in class too, and then I think I had most of you guys do 30 as well. So we don't get into anything new until we get to 31, 32. But again, I said I'd just do them all for you. I don't really mind. So let's do 29. It says the radius of a right circular cylinder is increasing. So they're giving us dr/dt. and we're increasing at a rate of 0.1, so that'll be positive. Now, this is a problem that says the height is decreasing. So this time, neither of those rates of change are 0. They're both actually changing over time. dH/dt is actually decreasing at a rate of 0.2, so make sure you make that one negative. They're asking what's the rate of change of the volume, so you're looking for dV/dt. Now, because all these rates of change are in play, we are going to need an R value to go with it. We're going to need an H value to go with it. We might need no, we don't need the volume. The volume ends up being not needed, but I'll write it down anyway. All right, so as I read through, it says, what's the rate of change of the volume when the radius is 2? Okay, cool. Then they gave me the volume, though. They said the volume was 12 pi. And I said, we don't really need that. But guess what? I do need H. So they've given you the volume so that you can use the volume and the radius to find the height. So before I start doing anything with my formula, volume equals pi r squared h, before I differentiate that formula, I need to kind of just go off to the side or on a piece of scrap paper or something, and I need to use that formula to solve for h. So if volume equals pi r squared times h, well, the volume is 12 pi, so I can substitute that in for v. Then I've got pi. They told me the radius was 2, and I'll square that. And so finally I've got this equation now that I can just solve for h. So I've got a 12 pi that equals 4 pi times h. So I'll just divide both sides by 4 pi. So you get 12 pi divided by 4 pi. And the pi's cancel, and 12 over 4 is 3. So we now know that our height is 3. And this measurement we needed. The volume can just go away. We don't need it anymore. We have all the stuff we needed. dV/dt is going to be our answer. So again, we differentiate, and we're differentiating remembering that we do have to do the product rule. So this is going to be dV/dt equals 2 pi r times dr/dt and times h, and then plus the pi r squared times dH/dt. So there's our big old equation, but we go ahead and just plug into it. dV/dt is what we're trying to solve for, so we'll leave that guy alone. Then we've got a 2 and a pi and an r, and we know the radius is 2. Then we've got dr/dt, which we were told is 0.1. Then we've got the height that we had to come over here and sort of figure out on our own. So we solved this little mini problem to find that our height was 3. Then we're going to add to that a pi times our radius, which is still 2, that's squared. And then dH/dt was this negative rate of change, the negative 0.2. Yeah, I think that all looks fine. Okay, so just do this math. You get dV/dt equals 12 times 0.1, so 1.2 pi. And then since this is negative, we're actually subtracting. 4 times 0.2 is 0.8 pi. And since these both have pi, they're like terms. So we can say that dV/dt is equal to 0.4 pi. And again, I don't really want us using decimals, so if we could shy away from that, that would be great. So 0.4 is literally 4/10. So you could just convert this to 4 pi over 10. Then you could reduce. And a slightly better answer to give here is 2 pi over 5. Now, neither one is wrong. If you gave me this decimal answer, you're not wrong because you didn't round the decimal off. It is still exactly precise and exactly correct. But I would prefer this. Let's turn that into a decimal now because I did want both. So it's 0.4 pi. I guess I'll just do that math. That's a little easier. 0.4 times pi is 1.257. And since that's the rate of change of a volume, make sure you give it to me as cubic centimeters per minute. But there you go. There's all three things that I need. I need the exact expression, I need the decimal approximation, and I need units. Okay, so 30 Yeah, all right. I feel like this is straightforward for the most part. It says the radius is increasing, so that's dr dt. And we're increasing at a rate of 2. It says what is the rate of change of the height? So you're trying to solve for dh dt. So dh dt is going to be question mark. We're being told that the rate of change of the volume. We're increasing at 100 pi, so that's positive 100 pi. Then they want to know, hey, what is this rate of change when the radius and height are both 10? So that means we'll let r be 10. We'll let height be 10. And we could find the volume, but again, remember, when we differentiate our volume formula, the v ends up not canceling out, but the v ends up getting processed and it's not there anymore. So I don't need to figure out the volume. The volume is not needed. So okay, same derivative. I'm sure, fine, I'll do it. The volume is pi r squared times height. So our derivative would be dv dt equals 2 pi r dr dt times h plus pi r squared dh dt. And I think we're just plugging in as we go, no big deal. Excuse me, dv dt is 100 pi. 2 is 2, pi is pi. The radius I was told was 10. The rate of change of the radius I was told was 2. The height I was told is the same as the radius, so that's another 10. Then you add to that a pi, a radius that is still 10, but squared this time. And dh dt is the thing we're solving for. Okay, so this 100 pi I'll just bring down. Now what is this? 2 10s make 100, and 2 2s make a 4, and 4 times 100 is 400. So that's 400 pi. Plus 100 pi dh dt. Now remember, for us, dh dt is our variable. It's almost like that dh dt might as well be a big honkin' x. So don't try to say that 400 pi plus 100 pi makes 500 pi. This is 100 pi x. So you can't combine this stuff that's over here on the right. That means our only move is to actually be subtracting 400 pi from both sides. We'll do that first, leaving us with negative 300 on the left-hand side. Negative 300 pi, I mean, of course. And then we've got the positive 100 pi as a coefficient on our dh dt. So now to isolate dh dt, we got to divide by 100 pi. That gets the 100s to cancel, the pi's cancel. We've now isolated dh dt. And we see that over time, to get the rate of change that we're getting, the rate of change of the volume must be negative. It's negative 3. Which means that for the first time, you don't have to give me a decimal, because this is coming out exact. Now it's negative 3, what? What am I solving for here? The rate of change of the height. And so the height then would be measured in centimeters per second, not cubic centimeters. So there you go. So yeah, so even though the rate of change of the radius is positive and the rate of change of the volume is positive, the rate of change of the height ended up being negative. That's 30. Here's 31. So 31 is a little different, actually. Okay. So, I wanted to try something a little different here. I don't know if anybody needs this. Obviously, skip ahead if you don't. But this question is talking about a right circular cylinder that's being flattened in such a way that its volume remains constant. That should probably sound to you a lot like somebody took a bunch of Play-Doh and they made a cylinder. let's pretend that's a good looking cylinder. It's not great, but it's fine. But as I take this thing, if I just took like a big old plate, like this plate, and I just squashed it down, then I'm not losing volume and I'm not gaining volume. It's the same hunk of Play-Doh, right? So what's going to happen as I squish it down? Obviously the height squishes down. Squish, I'm doing it. You can't see anything but my stupid hands. So this experiment was a failure. But hey, look at my cylinder that used to have the proportions of sort of a soup can. Now it's like a much smaller disc. As the height shrunk, the radius had to increase so that the volume stayed the same. And so you end up with sort of like a hockey puck shape now. So what I'm trying to say is just, for this problem, the one that we're talking about now, sure, I'm squishing it down. That means dH dt is going to be negative. But while the height squishes down, for the volume to remain the same, the radius has to grow. So dr dt will be some positive value. And what does that mean about dV dt? Well, we literally said the volume is constant. So that means the rate of change of the volume is 0. So in this problem, we're back to having a 0. But it's not the rate of change of the radius, it's the rate of change of the volume. dV dt is 0, while dH dt and dr dt are something. Okay, dH dt is negative because we're squashing it, but dr dt is positive because as we squash it, it goes burp and it extends in that direction. So hopefully that helps. Maybe it doesn't.